of quantum computing and just how to get involved with quantum computing in general. So with that, Emily, please take it away.
All right, thank you. Trying to make sure that you guys can see my screen here. This worked for me the other day.
We did a good test run, and things ended up working out.
Yeah. Okay. So I want to start this with a gigantic disclaimer. I spent a lot of hours preparing this, trying to figure out how best to express this concept, and I still don't think I understand it very much. So I'm going to do my best here. So take everything with a grain of salt. But this is an introduction to quantum computing. So for the first part here, what is quantum computing? So if we were to define quantum, if you think of the computer you probably have in front of you, it is referred to as a classical computer, and it stores encoded information in bits of 1 or 0. But a quantum bit is also called a qubit, and it represents subatomic particles. So it keeps a unique value, and it's very different from a classical bit. So a qubit, it could be 0, it could be 1, it could be everything in between. It's best defined by a complex vector space, for those of you who are familiar with linear algebra. So it's based on two basis vectors with two complex coefficients, which are called amplitudes. And those amplitudes are what determines the value of the qubit. So the state of a qubit at any given time is, again, demonstrated by this 2D space right here, with alpha and beta being the amplitudes. And also feel free to stop me at any time if you have any questions.
Wait. Let's go back to the sphere representation. I think the sphere representation of it is pretty neat. So when we say, I'm trying to process this myself because this is one of the most famous images you'll see when digging for quantum computing stuff, right? Is the sphere here. So straight up is essentially, I'm trying to just visualize how we would represent 1 in the quantum space, right? So the alpha and beta essentially are the two numbers that represent, it's a complex value, right? And that alpha and beta, I'm trying to rectify that with the sphere, essentially. So is the alpha one of the components of the alpha and beta, are the magnitudes of the components? But why?
So
why did
exactly.
they display? So I'm thinking in terms of linear algebra right now. So the basis vectors are 1 and 0, right?
Yeah.
Yeah.
So,
okay.
Yeah. So when you for this value right here, the basis vector of 0, that's like having a basis vector of 0, 1, and for the vector space of 1, that's like having a 2-digit vector of 1 and 0.
Right.
So yeah. And again, I'm gonna there's a little more information in the next few slides, but essentially qubit it encompasses both 1, 0, and everything in between. It's based on probability. And I'll get more into that, but it's a pretty good visual representation. So just like, well, very similarly to classical computing, quantum computing also involves quantum logic. So it does look a little different from your standard and or nor not gates, but it's sort of similar in that you can use these gates to apply logic to quantum bits and manipulate them, which ultimately allows quantum computers to run their algorithms. And in quantum computing, there are two main I'm trying to think of the word here. Quantum computing essentially is based on quantum mechanics. And there are two main principles of quantum behavior that especially apply to quantum computing. And those two are superposition and entanglement. Superposition is what I was trying to encapsulate by describing a qubit as representing 0, 1, and everything in between. So a qubit in itself is very holds the probability of any value between 1 and 0, and it is also a very fragile state of information because it is based on actual subatomic particles such as photons or electrons even. So once you actually try to measure the qubit to determine what state it's actually in, the qubit collapses and assumes a value of either 0 or 1. So similarly to quantum mechanics, qubits, when involved in a state where there are multiple qubits acting together, they can be observed with wave-particle duality. They can either act as, as a particle or as a wave. And I'm sorry, I'm really trying to. I feel like I'm not explaining this right, but one of the explanations that I found was really useful was that when explaining superposition, it's not so much a description of 0 and 1 and everything in between, or alternately 0 or 1 or everything in between. You can't really compare the position of or the value of a qubit to standard logic, because quantum behavior doesn't really simulate real world behavior, which is something that is more studied in physics. So it's not so much an and or situation as much as it is it could be any value between and including 0 or 1. But anyways, that's one of the most important topics. The second one is entanglement, which is a phenomenon where two or more quantum particles, regardless of distance separating them, can be entangled, or in other words, they're generated in a way such that the state of one particle in the system can't be described independently of the state of the others, even when separated by a large distance. This can be demonstrated where if you have one particle that you measure and you find that it's either a 0 or a 1, the other particle with which it's entangled, that also collapses when you try to measure the first particle. And Einstein actually referred to the phenomenon of entanglement as, and I quote, spooky action at a distance. This is caused by the microwave signals that are imposed on subatomic particles, which also allow for the superposition to occur. So I hope that makes sense. Are there any questions about either of those two concepts?
So entanglement can occur over incredible distances, right? It's kind of and it happens instantaneously, right? So when the position of one entangled particle collapses, you instantly know the state of the other particle, no matter how far away it is, right? And that's the whole incredible thing and why Einstein had to call it spooky action at a distance. But in reality, it doesn't break causality because despite the fact that you know what the other particle is, it doesn't mean that you've somehow altered the particle faster than the speed of light. It's just that it wasn't known until you collapsed the state of the particle that you had, right? So that's one of the things that people like to think about when they think about entanglement. And entanglement, especially entangled qubits, are one of the main things people are looking into right now with quantum computing, because the potential of entangled qubits, there's a lot of wide-ranging applications that we can talk about later if we want to get into it. But back to you.
I think that's a great contribution, actually. That there's going to be more on entanglement later, but it does contribute to how quantum computing can function with qubits and how that sort of aids in the computation. Two smaller or maybe slightly less significant properties of quantum mechanics are interference as well as coherence and decoherence. So interference, it can be used to control quantum states. And this is in correlation with the wave-particle duality found in superposition, where the waves of the wrong answers of qubits, you're able to control the wrong answers and to sort of shoot the waves into each other and cancel out or negate the incorrect states or the wrong answers, as well as when you have waves of right answers, you can use that to sort of amplify the right answer, which then contributes to the probabilistic result. And in coherence and its opposite, decoherence, quantum systems are extremely sensitive to error, which is also referred to as noise, as well as environmental factors. For example, quantum computers have to be kept at sub-zero temperatures, quite literally colder than outer space. So these qubits are essentially limited in their lifespan. And so this is something that is important to consider with quantum computing when trying to optimize systems and prolong life of the quantum computers through algorithms and reversibility, being able to use quantum computers for more than one purpose. Any questions on interference and coherence? All right. Now, how do quantum computers work? So a quantum computer takes input as some quantum or classical state. This is possible because quantum computers can accept classical states just as much as they can accept quantum states, because a classical bit of 1 or 0 is a possibility for the state of a qubit. So a quantum computer will accept the input of a quantum or classical state, and then it will perform manipulations or transformations on the amplifiers, which were the A and B of the qubit state. And those ultimately affect the probability of whether the qubit is a 1 or a 0 at any given time. And then the output is a probabilistic function of how likely it is that the qubit is a 1 or a 0. And so this is all achieved using the quantum versions of classical logic components, such as quantum gates and registers. So in order to achieve, so you're getting these probabilities as your answers. So in order to get a more accurate result, this cycle is repeated, and just almost predictably with any sort of probability, the result does tend to differ even slightly as you repeat the cycle, but more or less, the more you repeat the cycle, it does get you closer to the correct answer each time. And in order for a quantum computer to function, the qubits must be in a correct state for a given problem, which can impact the quantum computer in functionality and overall life as well. In this picture over here, this is the IBM Q Quantum Computer. I think it looks really cool. I watched a video on it, and one of the developers described it as a chandelier, which I can see. So down here at the bottom is an exposed part. That's where the microcontroller is. And all of the fancy stuff on top, that's mostly for maintaining the whole system. Sort of like how I mentioned that the qubits are extremely vulnerable to environmental factors. So the majority of these wires are all involved in cooling processes. I know also some facilities that have these quantum computers, they'll have concrete floors that are a meter thick to try and prevent any sort of like vibrations from setting off the computer at all. And this particular computer relies on microwaves to control the qubits as well, sort of like how I mentioned earlier. So the important thing for you to understand is that quantum computing isn't just a matter of trying all the answers in parallel. So it's a common misconception that comparing quantum to classical computing, it's not so much a faster way of computing as it's a completely different form of computing. It's like comparing a car to a carpet. the whole idea of quantum computing is to organize a pattern of interference. So the paths to the wrong answers will cancel out, and the paths to the right answers will strengthen each other. So quantum computers, yes, they might be a little faster than classical computers, but they can also do more than classical computers. It doesn't really seem like classical computers will become obsolete anytime soon. They're still good enough for most applications, and quantum computing is a little too new in development to really be sustainable. But it's not so much a faster. It's not so much a way of trying all of the different answers in parallel and coming up with the right answer, as much as it is a different way of getting to the answer.
Emily, there was something I wanted to bring up too, on that point, that about classical computers being quote unquote obsolete, like that not happening. A good example of that I heard was from, I was reading something and pretty much said like there are a decent amount of cases where using a classical computer for a certain algorithm would actually be better than a quantum computer. And I heard, for example, like they try to compare it like this, like think of something like quicksort versus insertion sort. For a small amount of data, insertion sort is more optimal to use rather than quicksort. But in most cases, like you know what I mean, in different cases they have their different strengths. Is that kind of like how classical versus quantum would be?
Yeah, I'd say so. Yeah, it's sort of like two different ways of getting to an answer. Yeah, that's definitely a good point, and I think I touch on that a little bit later too. Okay, so a little bit about the history of quantum computing. So one of the first developments in quantum computing goes back to 1968, when Stephen Weisner invents conjugate coding, which it can be described as an extension of a random number generator. It's used in the as early as the 80s in cryptography. And it was very ahead of its time, and so it was originally rejected. But the use of it in the 80s for cryptography went on to sort of motivate further discussion on the possibility of quantum computing. In 1981, Paul Benioff describes the quantum Turing machine, which is also called the universal Turing machine. So this is the first quantum mechanical model of a computer, and this event is sometimes referred to as the start of quantum computing. So a universal Turing machine, it generalizes Turing machines efficiently, and it shows that reversible quantum computing was possible, or to put it another way, a computer can operate under quantum law. Also in 1981, Richard Feynman, he's a notable physicist. So he's got a lot of work related to quantum mechanics. He first coined the term quantum computing. He believed that that quantum computing could accurately simulate quantum behavior as it exists in real life, but he also recognized that it would be impossible to simulate a quantum system on a classical computer. And Fun fact about Richard Feynman, great mind, super smart. His second wife, Mary Louise Bell, divorced him because, and I quote, "He begins working calculus problems in his head as soon as he awakens. He did calculus while driving in his car, while sitting in the living room, and while lying in bed at night." So this guy was very passionate about his work. And he contributed to quantum computing a lot throughout his life. All right, so in 1985, David Deutsch describes the universal quantum computer. And so this is similar to the quantum Turing machine, where the universal quantum computer is able to simulate any other quantum computer with worst case polynomial slowdown. So ultimately, you could simulate the entire physical world with the universal quantum computer. Very powerful model. And Deutsch also contributed a lot to computer science. Part of his research was where the power for quantum computing comes from. And he believed that it could only be explained by the many worlds interpretation of Hugh Everett, which, to sum that up, when a quantum computer performs a computation, the result is computed in different universes at the same time. And I personally have not looked any further into the many worlds interpretation, but that sounds pretty freaking cool. And then in 1994, another important development, Peter Shor of Bell Labs in New Jersey, he discovers Shor's algorithm, which is used for integer factorization. And this is a big deal because it kickstarts an interest in quantum computing and really creates a drive to start developing more. So when considering integer factorization, it's impossible to calculate on a classical computer. It takes billions of years, literally. And for that reason, integer factorization is used in the encryption of RSA, which is the encryption method used in storing personal data digitally and in websites as well. So this is a really important discovery. Currently, using a quantum computer and Shor's algorithm, they've only factored up to 21. And medium security RSA has roughly 1,024 bits. So we're not really close enough to breaking RSA encryption, but that is something to consider as we develop quantum computing some more. Okay. So as for where quantum computing is now, so the majority of quantum computers use particles such as superconducting circuits and also photonic circuits. As for how the industry is sort of developing, the majority of focus is on sort of improving algorithms, trying to scale down these quantum computers. I can't remember the name of the company, but I know there was one company who earlier this year announced that by the end of the year, they were going to release a quantum desktop computer. So that would be a pretty significant feat if they're able to do that by the end of the year. We're not quite there yet, I don't think. Also improving stability of current quantum computing models, and also researching sort of alternative classical models. How can we improve existing technology? Because quantum computing, as of right now, is very difficult to sustain. And when actually developing quantum programs, the majority of the work is done on cloud-based servers, which I will cover later. So it's a little out of reach for a lot of current applications. As for significant recent events, in 2014, the WikiLeaks confirms that the NSA is working on a quantum project to crack RSA encryption. And as well, there are claims of quantum advantage. And quantum advantage basically claims that a quantum computer can do something in seconds that takes a classical computer, billions of years. So it's kind of like the top tier of efficiency when it comes to quantum computing. So in September 29, Google claims that their quantum computer Sycamore reached quantum advantage with 54 qubits. And in December 2020, the University of Science and Technology in China developed Zhujiang, which has 76 photons, and they claim that that also reached quantum advantage. However, as to the validity of either of those claims, it's still a little fuzzy. But it's certainly a significant feat. Here is just a basic graphic on 3 different types of quantum computing models. The first one on the left over here, the quantum annealer, that's one that is currently being developed to try and improve. It's currently the least powerful model of quantum computers, but it's often used in business applications, and it's the least difficult to develop. And then over here on the right, we have the universal quantum machine, which is very, very powerful, but it also is very difficult to maintain. As for the future of quantum computing, it's really hard to estimate because quantum computing is, again, such a new concept and largely underdeveloped that it's really hard to predict where it'll be in the next 5 years, next 10 years. One consideration when it comes to quantum computing is Moore's law, which is traditionally applied to classical computing. And Moore's law states that the number of transistors in an integrated circuit doubles roughly every 2 years. And the point of this is it reduces the size of the microchips and the size of computers. So as to whether or not this will apply to quantum computing is a little, it's definitely debated. For one point, it might not apply to quantum computing, as quantum computing already deals with subatomic particles. So you can't really get much smaller than that. However, quantum computers are also unprecedented in technology. So as to whether or not we would be able to apply or observe Moore's law with quantum computers and get them to be really, really small, that's yet to be seen. But in order to make these quantum computers smaller, we would need to increase the number of qubits and also decrease the error rate or the noise on the qubits. So as for quantum computing, further development on practical applications, which I will cover, also developing quantum software. So even if we have only a handful of quantum computers kept in labs that we access over the cloud, being able to utilize those machines with software kits would be important. And also teleportation. That's actually something that's been demonstrated by quantum computers already. Of course, it only applies to subatomic particles, similar to entanglement. It was heavily based on entanglement, where two qubits, which were separated at very large distances, they were able to transport or teleport the entangled qubits to the to its pair. So that would be really cool, I think. But we're not quite at full-scale human teleportation yet. All right, so moving on to how we can use quantum computers. So there are a ton of different applications for quantum computers, most of which essentially comes to not so much everyday applications, but medical fields, data analytics, basically optimization of any field, really, especially machine learning and AI, cryptography, digital security, healthcare. I mean, researchers are already looking into ways to use quantum computing to both detect and detect cancer cells. So that would be an important application there. As well as climate change, financial services, blockchain as well. It can really be applied to a lot of different things. And beyond those applications, quantum computing is for everyone. You can code quantum programs in Python. Rigetti has developed a open source Python library called PyQuil that's used for quantum programs in conjunction with their quantum virtual machine, which is also known as QVM. IBM has done a lot of work in the field, and actually I'll show you in just a second the Quantum Composer. But they also have a very popular open source software kit called Qiskit, and that's can also be used with Python for working with circuits as well. Microsoft they have developed their own quantum-focused language called Q Sharp. I'm starting to notice a pattern with Microsoft's languages, C Sharp, F Sharp, Q Sharp. But they use that with their quantum virtual machine as well. And they also have a service with their product Azure, which is a collaboration of different quantum servers with different companies, as well as different optimization services as well. So it's trying to, I guess, combine resources to really optimize quantum performance. And you can use that with your own code. I don't know if that's something that is included with the Microsoft subscription that we get through UAlbany, but it's possible. Okay, so demonstration time. So IBM Quantum Composer is a very, very cool tool. It's a great graphical visualizer for quantum behavior. And I suppose this makes a lot more sense if we were to talk more about the actual logic gates and operations and the math behind quantum computing. But all of these represent different operations that you can drag and drop, and it affects the probabilities. You can see, I mean, this right here is just a logic gate, so that's not going to do anything, but it's really interesting for trying to express the probability of qubits and the results, as well as over on the side here. These are actual, if you wanted to actually code the program, you could do that as well. And I guess as another example where there's an actual algorithm displayed, this is the Bell state, which is Bell state demonstrates entanglement. So it shows that after you measure the states of each of these qubits here, then the other one here collapses as well, and the probability is affected. Usually when you have two qubits in entanglement, they will share similar properties such as spin, polarity, speed, all properties that are applicable to quantum particles. And so oftentimes you'll see entangled bits will also share the same state when measured. So that's a pretty cool way of making quantum computing accessible, I think, especially in terms of visualizing, because personally, I'm a visual person. I had to watch a lot of YouTube videos until I started to wrap my head around this. And I have a quote here from Richard Feynman. In conclusion, I think I can safely say that nobody understands quantum mechanics. And that's probably accurate. If you don't understand it, you're starting to understand it, I guess.
I have an even better quote from Peter Shor. who did Shor's algorithm. So I actually have a funny story about Peter Shor. So I randomly one day went on Stack Overflow and asked what the word was for someone who doesn't really understand something, but pretends that they understand something. So when someone says that they understand how a car works, when in reality all they know is what an engine is, I thought there would be a good word for like someone like that. And I asked that on the English language Stack Overflow about computers. I said, "What's a word for someone who doesn't really understand what a computer how a computer works, but pretends to understand how it works?" And lo and behold, Peter Shor, the Peter Shor who discovered the quantum computing algorithm for breaking RSA encryption, responds to my comment and says, "Nobody understands how computers work." Which, to get that from the leading expert, one of the leading experts in quantum computation, if he doesn't think people understand how computers work, I don't think anyone understands how computers work. And I think when we combine that with Feynman's quote here about no one understanding quantum mechanics, and Shor saying no one understands computers, I don't think anyone understands quantum computers even more. So it's definitely a very complex field. And for those of you who are interested more in the mathematics of it and the modeling of it, we last semester we did a workshop on it where it was a watch along. And I'll link the video that we watched. There's a great talk by Microsoft Research. So Emily showed off a bunch of those quantum gates before. And those quantum gates, you kind of have to understand the linear algebra of it to fully appreciate what's going on. That each of these quantum gates can be represented by these matrices, essentially, on this slide right here. So when we actually took a look at the quantum computer, and there was those lines, right, the quantum computing line diagrams with all of these gates, right, what's actually happening is we're just applying sequences of matrix transformations to these qubits and putting them into entangled positions. And there's a really good talk by Microsoft Research that explains how this happens, and I'm gonna link that in the chat for us, because that is a very good resource for those of you who want to dig more into this after this workshop. Quantum computing for computer scientists. Here we go. And I've dropped that in the workshop text channel. So if you really want to dig into how all of these gates work, and you want to dig in a bit more to the linear algebra side of things, it's really cool to see a real application of linear algebra outside of the classroom and in this quantum environment. Because all quantum computing is just a bunch of linear algebra. So yeah, it's very neat to actually look a bit more into the math behind everything.
Yeah, that's great. And I know I came across a couple GitHub repositories of like tutorials on quantum computing. Like some of them were in Jupyter, but very, very intensive step-by-step tutorials that really helped you understand or like start quantum computing. So I will also link the ones that I found after the presentation. So, does anybody have any questions? James makes a very good point. Linear algebra is such a big part of quantum computing, so is physics. You really have to understand quantum mechanics in order to apply it to computing. So there's a couple different layers to this, but yeah, if you have any questions, I'll do my best to answer them.
You're telling me everyone here understood everyone understands quantum computing perfectly?
I'm not saying that.
That's what I'm hearing. I'm not hearing anyone talking, so I'm hearing a lot of understanding of quantum computation.
No, but you said if we're not understanding it, then we're gonna understand it. So therefore, you know.
Actually,
I
that brings up a good point too with like the linear algebra stuff. James, I know we were talking about how Albany, when we teach linear algebra, we teach it like strictly as like mathematics, and like there's really a couple of sides to that when it comes to linear algebra because you have all these applications for linear algebra, like as programmers, computer scientists, engineers, whatever, you have that side, and then you have like the purely mathematical standpoint. You have like things in economics and etc. We don't really appreciate, even if you take linear, and I definitely feel that the applications, because you spend like a chapter on that in linear, and it's not even that extensive. You probably spend like a section on it for like computer graphics or whatnot, or anything like this. So it'd be nice to maybe do like something like on that. I don't know.
Yeah, there's that we don't teach. I unfortunately here at Albany, the linear class is very, very theoretical and nowhere near as application oriented as it should be. Linear has a lot of applications in a lot of areas that we don't get to experience. All of machine learning, every single machine learning model is basically modeled as a sequence of matrix transformations as well. At least the basic ones are. And quantum computing as well. All of your quantum algorithms are modeled as a sequence of matrices transformations. And in data science, almost all of your data transformation algorithms, PCA and everything, is modeled as a sequence of linear transformations as well. So there's a lot of like serious applications of linear that we just don't get to look at here in our linear classes. Our linear classes are very basic, and there's really no good introduction and nothing to bridge the gap between these applications and the theoretical class that you take like either freshman or sophomore year for linear. Yeah, so I would say it would be very nice to have that.
As an addendum, when considering superposition, think of it like Schrodinger's bit. Once measured, like it's before you measure it, could be anything, and then once you measure it, it's either a 1 or a 0. So I don't know. That was something I forgot to mention earlier, but
I was thinking about that when you were talking about it. I didn't say anything though.
yeah.
You're talking about Schrodinger's cat, right? How it could be alive or dead.
Yeah, yeah.
And so because it could be alive or dead, it's classified as both.
I think so. I don't know. I think I understand the concept, but I've never really I don't know how to best describe it.
You got the main point down. I mean, that's pretty much.
Yeah.
Anything about it. I don't know as well about like the the more deep features of it, but that's the general consensus.
And I guess not to jump around, but to go back to your point about the practical applications of linear algebra. I mean, based on the current applications of computers to mostly integer factorization, it's basically like using linear algebra on a much larger scale. Like the quantum computer that was developed by the university in China, that one, it solved a Gaussian, some form of Gaussian equation or transformation. They solved that in 200 seconds when it would take a classical computer upwards of 100 billion years, literally. So that was, I mean, I think we covered Gaussian in linear algebra at least a little bit. So it really is like just using linear algebra, but on a much larger scale.
Yeah, the Gaussian elimination algorithm to make matrices what are they in reduced echelon form, right?
Yeah.
I'd like to show
I don't know.
everyone some quantum magic on the quantum computer simulation, if we have a chance.
Sure, yeah, go right ahead.
Okay, this is an extraordinarily simple demo that I hope somewhat can demonstrate the idea of qubits. So essentially, we start off with this line, right? So this line represents a single qubit and a sequence of operations that we're performing on our qubit. Now, our qubit can be thought of as a probability distribution that collapses to either a 0 or a 1 at the end of its lifetime. So this chart down here, this probability chart right here, can everyone can see this, right? I'm live. Yes? No? I'm pretty sure I'm live. Okay, yeah, I'm live. Good. So since everyone can see this, so this chart right here, this shows what we're collapsing to. So by default, this is going to be our 0, right? We can see on our quantum sphere that this is a state 0, and the probability that we collapse to 0 is 1, right? Because it's 100% chance we're going to end up with a 0, right? So the way that we actually put something into superposition is this first guy right here. This is the most important thing we have, the H gate. This is the Hadamard gate. Someone is echoing. Who's echoing? Okay, I don't think anyone's echoing anymore. Okay, so the way that we actually put something into superposition is this H gate. This takes our current 100% of getting 0 and basically splits that in half. So now we're in superposition. Now our bit, when you hear people say, oh, in quantum computing, your bit can be both a 0 and a 1, this is what they're talking about. There's a 50% chance that at the end of this algorithm, our quantum bit Q0, is both a 0 and a 1 at the same time here. So if we measure at the end here, it has to collapse into something. But see, so when we measure here, essentially, it's always going to collapse into a 0 because measurement forces a collapse. But at the time after this algorithm executes, this bit is still in quantum superposition. It's either going to be a 0 or a 1 until we measure it, and then it's forced to collapse into a 0 or a 1 50% of the time, right? So that's the idea of it being in two positions at the same time. And we can see that on our sphere here, right? That we have 50% of the time we're going to be a 0, 50% of the time we're going to be a 1. So now we're in our superposition. But here's where things start getting really cool. We can perform operations on our superposition bit and then unsuperposition it with another Hadamard gate and then get the result out. So keep in mind right now, so our quantum bit, we start out with a 0, right? We're starting out with the 0. Like if I delete this, 100% of the time we're going to be a 0, right? Now let me invert it real quick. So if I invert it 100, this is an inversion. This is a NOT gate, right? This makes sense. Like not 0 is 1, right? Everyone understands that, right? The opposite of true is false. We all understand this. The opposite of false is true, right? So that's all this does, right? This gives us whatever it's not. But here's where things start getting really weird. So we put our quantum bit into superposition, 0 and 1. 50% of the time it's going to collapse to 0. 50% of the time it's going to collapse to 1. Now we not our superposition bit. And as we can see, because we're in superposition, nothing has changed so far, right? We're still 50% of the time going to be 0, 50% of the time going to be 1. But now we're going to use our Hadamard gate to turn back into a normal bit. And now watch this. It's going to be 0 when it collapses, which I actually did not expect. What happened? This actually worked last time, and now it's not working. It's supposed to collapse to 1. What are they doing to me? They're ruining my demo. I'm so sad. All right, let me figure out what I've done wrong here, because clearly I've done something wrong. If I add more bits.
It's okay if you don't understand it.
I had this demo planned out perfectly. We were going to collapse it back to its original state, and then they lied to me. All right, I do my switcheroo with the NOT gate, and then when I try collapsing back, it's supposed to collapse to a 1, but it's collapsing to a 0, and it shouldn't be. What if I put in 0 by default? Are we going to collapse then? No? They're trolling me. I'm so sad. This literally just worked when I did this demo right before this, and now it's not. Oh, wait, is it because... Oh, it's because I'm not... Is it because I'm not measuring? I'm so sad. It's always going to measure as 0, even though we're doing the inversion on the quantum bit. This is obscene. I'm very sad. My demo's been ruined, everyone. I'm sorry. I wanted to show that we could perform quantum operations, and it has fallen apart due to IBM Quantum Composer being not nice to me. I can attempt to reset. Am I using the NOT gates right? I feel like I'm using that wrong. I just did this demo, and it's very upsetting. Well, you know what? I guess this just goes to show that nobody understands how quantum computing works. How sad. Let's see. On Hadamard.
Well, at least thank you for showing us a little more about how that works. I found it, but I didn't have the time to actually figure out the gates and everything.
Of course, yeah. It's extraordinarily painful. Wait a second. Do I have to invert before going in? Let me. Okay, if I invert before going in, then I Hadamard, then I Hadamard again.
Check workshop text.
Let's check workshop text. You are Hadamarding, so your first bit is always going to be you invert and then you double Hadamard, which essentially should just unquantize it. It should measure it technically, I think. I mean, it seems legit. I think I'm trying to figure out what you're doing, because your double Hadamard is basically guaranteeing your 0 to become a 1, right? Unless I'm beyond confused. Wait. No, because you're inverting 0 and you're getting a 1 on the first one, and then you're double Hadamarding on the second bit. Okay, I'm trying to figure out why this demo isn't working as it's supposed to. I'll figure it out eventually. Probably won't be during this workshop, though. That's for sure. All right. I think that's all for my demo. Definitely watch the video that I sent if you want to try and understand this more and understand these quantum circuit diagrams, is what these things are called. It's a lot of fun to play around with these. Back in the day when I actually understood how this worked, I had a lot of fun with it, and just especially some of the entangling examples are a lot of fun to mess around with. And there's also quantum Python and everything, so I hope all of you guys have fun with that. So I'll let you guys know if I can get my quantum example working later on tonight. But with that, I'll give it back to Emily for any other questions that anyone might have.
There's somewhere we can download the slides from?
Sure thing. Yeah, I'll drop it in the chat.
Yeah, and I'll try and upload everything. We can upload any of our workshops to GitHub this semester, even though I wanted to have all of our workshops uploaded to GitHub this semester. But it's we should end up getting everything on there.
You might have to view the slides in presentation mode, though, because I use some fancy effects on a couple slides, so it's a little overlapped. But I mean, there's a ton of sources at the bottom. I thought they were all pretty interesting. I feel like I'm not accurately conveying this well enough, but after pouring hours into almost pulling my hair out, I am actually kind of excited about this. I think it's really cool. I think you should check it out. I think
everyone should be excited.
Yeah, I'll especially drop the links for the Python libraries and stuff. It's really not. It's not hard. It's definitely doable if you wanted to try a little bit.
Yeah, there's a lot of great resources out there, and also Q Sharp is pretty cool to check out. They have a very intuitive way of looking at things. There's a lot of quantum emulators out there as well. It's a lot of fun to play around with, and I recommend. Again, the video is great. Does anyone have any questions? Because we can still answer questions if anyone has anything. Otherwise, we can wrap things up. I take silence as everyone understanding quantum computing, and it's glorious. It's exactly what I like to hear.
No,
If you don't
No,
understand,
you're-
then you are
I
do
fully understand it. I am now a professional in quantum computing. I'll be building a computer in 3 days. You'll see.
That's what I like to
Hey
hear.
man,
That's exactly
I don't
what
really
I want to hear.
understand,
Alright, so expect
but
the
I
news to come
understand that
out.
it's hard to.
This is what we like to hear. It's a very
It's
complicated area.
Like I understand that it's basically impossible to like fully understand,
Yep.
which is normal.
that's a lot of things, though. I mean, so one cool application that we have from quantum computing, so first of all, the integer factorization, right? Breaking RSA encryption with a real quantum computer. And then on top of that, we also have, for everyone who likes your searching algorithms, there is a O of n square root time search, which is incredible to be able to do a search in square root time on unordered data. So definitely look into some of that. Like there's a lot of cool stuff that you can do here. So definitely be sure to check some of this stuff out and check out all of the other stuff. With that, Emily, do you have anything else before we wrap up?
No, that's that's pretty much what I got here. Thanks for coming, guys. I know I had fun. Sorry, I hope I explained it well enough. Kind of jumped around there a bit, but yeah, I hope you get something from this.
Yeah, so thank you for coming, everyone. Don't forget to go vote. If you haven't voted already, go vote like right now on my involvement. The link is literally in general chat. Thank you again, Emily, for giving the quantum computing workshop. Emily was not required to give a workshop this semester, but they decided to do it anyway, which is exactly the kind of motivation we're looking for in our D-Board members. On top of that, just to reiterate the schedule for this week, tomorrow night we're going to be having our kitware panel, which is going to be really exciting. We're having kitware come in. For those of you who don't know, kitware, they developed CMake, which is like the #1 C and C++ build tool on the market. If you go into industry and just as like a normal software developer and are doing any work with C or C++ at all, you will be using CMake. And tomorrow night you have the opportunity to meet the people who made CMake and listen to some of the stuff that they're doing. So there's a lot. It's going to be a very exciting event. If you're going to come to, I say this for a lot of events, but if you're going to come to one event the entire semester, tomorrow night is the event to come to. On top of that, Friday night, we're having side project development night. Monday night, professional development night. We're going to be doing resume review and whiteboard interview practice questions, as always, from Code Wars. And then next Tuesday is our officer meeting. So officers, get ready for that. Matt is going to be making the schedule for that. So Matt, remember, did Matt leave or am I blind?
What classifies as an officer?
The number one, not you. Yeah, he left. Wow. I'm going to have to add him later. What a noob. Okay. So with that, then, yeah, we're still... Oh, I'm having a workshop next week. The workshop I'm hosting next week is going to be the most important workshop of the entire year. So you absolutely have to come to it. No exceptions. I can't spoil anything. No, listen. It's the most important workshop. It's on April Fool's Day. That doesn't mean anything. It's the most important workshop.
Oh my god.
It's the most important workshop of the entire year. I'm going to be teaching everyone the most important programming language that they've ever learned. Okay.
Oh no, here we go.
Listen, it's by far. Listen, you guys, everyone at this school is sleeping on what I'm going to be teaching next week. Okay, so I want to see everyone at that workshop because the industry is eating this up. It's hot right now. You guys don't know what you're missing out on, and I'm going to be teaching it next week. So
It's
by
Java,
all
right?
means, please, no, compared to what I'm going to be teaching. Java,
like a salesman for a product you don't believe in, James.
Java is child's play. Anyway, I'm hoping to see everyone at the workshop next week, and I'm hoping, but for real, I'm hoping to see everyone at the event tomorrow. Emily's going to be moderating that. It's going to be glorious, and you can ask questions to the Kitware people, which is great about the work they're doing, about the industry and everything. So by all means, definitely come to that. And then hopefully we'll see you at some of the events next week as well.
Yeah, also just want to put that out. Kitware, everything is open source. Even if you don't understand it, you want to just look at it, just look at it. I've read it a few times. I don't really understand a lot of it, but it's fun to just go back and take looks. And if you want, after you try to understand it, maybe you do, try to contribute. It's cool.
It really is cool. Everyone should try and look into open source. It looks great on their resume. And with that, I think we are... Does anyone have anything else they want to add on before I dismiss the meeting? I'm going to take that as no. Thank you for coming, everyone. I'm sorry my quantum demo flopped that I tried to do on the fly. But yeah, have a nice night, and we hope to see you at some of the events. And don't forget to vote. Bye-bye.